All right, good morning. I shall begin. Um, okay, so we're talking about tangent bundles, and so last time we um, defined what the tangent bundle was. It was the collection of all the tangent spaces of a manifold, and we showed that the tangent bundle was a vector bundle, and we did this in our explicit way um, by so we start with a manifold and an atlas and a chart in that atlas. And then for that, we built a chart for the tangent bundle. So like so. So the chart domain was the collection of all the tangent spaces over the chart domain for the manifold chart. Um, the chart codomain was simply the product of the chart codomains, and then the mapping, the chart mapping, took a tangent vector with a base point in u phi and mapped it to this thing. And so it maps it to the point in the chart in the first component, and then the derivative of the corresponding curve at zero as the second entry. And then what we proved last time was that if you did this construction uh, for all charts, then what we get is a vector bundle atlas. Okay, so we saw that there was a vector bundle structure for the tangent bundle. Okay, all right, so there's all the basic stuff about tangent bundles that we're going to talk about. So now what we'll do is we'll start talking about what are known as higher order tangent bundles. Okay. Um, all right. So the idea here is rather like the idea for a tangent bundle, except you consider more derivatives than the first one. Okay, but what we'll see is that the structure is not the same as the structure you got with the tangent bundle. Okay, so let's start at the beginning. Okay, so when we define tangent vectors, we defined a tangent vector as an equivalence class of curves. All right, so we're going to do a similar kind of a thing, just the notion of equivalence will be different. So we have a manifold. And uh, so we have, we're going to choose now a k. K is going to be the order, and k will be less than or equal to r, which will be a positive integer. Okay, so you choose an r, and then you choose a k, which is less than or equal to r. Okay, and let's choose a point. Okay, so given all of that, so we need to look at the kinds of curves that we're going to talk about. So an f k k curve at x naught. Okay. So previously we talked about curves at x naught. Okay. So now we have fk curves. And so the idea of a curve at x naught was that it was a C1 curve that passed through the point x naught at zero. Okay, so now it's simply going to be a CK curve that passes through x naught at zero. Okay, so it's going to be gamma. Okay, and so I, just like previously, is going to be, so we're going to talk about possibly complex curves here. And so again, remember that I was the complex generalization of an interval. Um, um, and that means a connected open set with 0 in I. Okay, so that's what I is, and gamma at 0 is equal to x naught. So the only difference here is that it's not a C1 curve, it's a CK curve. That's the only difference with what we had before. Okay. 2 FK curves, gamma A, let's say, from IA into M at x naught. Okay, and there's 2 of these. Okay, and I'll say that these are equivalent to order K. If, and the definition is rather the same as the definition that we had for equivalence of curves when we defined the tangent bundles in the case of K equals 1, and that is if for every admissible chart u phi 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 about x naught. All right, so the condition for equivalence of curves, C1 curves, was that the local representative of the curve the two curves has the same derivative. Well, here we're going to ask that the local representatives have the same first K derivatives. Okay, so phi gamma 1 j, all right, so that's the jth derivative, is equal to phi gamma 2 j 0 for j going from 1 to k. So what else could it be? All right. And then a kth order tangent vector, just like a tangent vector was an equivalence class of curves, so a kth order tangent vector is an equivalence class of FK curves. Okay, so a kth order tangent vector at x naught is an equivalence class of FK curves. All right, so with, of course, the equivalence relation that I just defined. All right. Okay. And so when we talked about these same ideas just for tangent vectors, the first thing we did right away was we showed that it's not possible that you could choose. So the definition says that for every chart, this is true. Okay, and so then of course the question is it possible that this can be true for one chart and not true for another chart? And the answer is no. And we did that in the K equals 1 case. And how do you do it? You just use the fact that the overlap or this expression involves the difference between these two things, when you represent them in different charts, they're equal because sorry, I'm again trying to say something in words mathematically that's easier to write. Say something in words that's easier to write down. To prove that equivalence is independent of chart, what do you have to do? You have to choose two charts. So phi u phi phi v phi and uh, u psi psi v psi be two charts. It's not. Okay, and what do you need to prove? You need to prove um, that, so let me give myself some space here. So you need to prove that um, these, and here J, of course, in both cases goes from 1 to K. All right. And so what did we do in the K equals 1 case that you can still do in the K equals 2 case? Um, you simply write psi. Okay, so I guess I'm still using an English language sentence here, so let me continue it. And prove that this is true by noting that psi composed with gamma 1 j is psi composed with phi inverse composed with phi composed with, and I don't need 1 here, I can have a and 0. Okay, just by sticking in phi and phi inverse, this so-called insertion of charts argument. And so sorry, not prime, but okay. And so then what do you end up doing here? You end up using the chain rule. So when j is equal to 1, it's just the first order chain rule, and there's an explicit then that relates the first derivative of this with the first derivative of this, and the relationship is an isomorphism, a linear homeomorphism between the two representations where this lives and where this lives. Now, for higher order derivatives, this is where things get complicated. Uh, because if you're going to prove that equality here implies equality here, you need to get a bijective correspondence between the jth derivative here and it's not really the jth derivative, it's the first k derivatives. Okay, so you prove that this is equal for every j going from 1 to k, if and only if this is equal for every j going from 1 to k. And you do this by induction on j. Okay, so for j equals 1, this is the tangent bundle case. And then for j equals 2, well, then you have to use the formula that relates the second derivatives. And we've talked about that formula. Um, uh, um, and and that formula is really the so-called Fodor-Bruno formula, which is the um, formula for the composition derivative of a composition of mappings. Okay, and the Fodor-Bruno formula, which gives Okay. So I'm not going to write it out explicitly. I'll just kind of tell you what it looks like, which gives psi composed with gamma A, J at 0, okay, is a linear combination of terms of the form D L, let's say, of the composition. Okay, so it's the chain rule. And so I'm composing this thing with this thing. Okay, okay, composed with phi at phi of x. Right? And then this thing has now L vector arguments. Okay, so let me abbreviate these. L arguments is, let's say, V I1 up to V I L. Okay, all right, where V I1 up to V I L are vectors of the from the following set of vectors. Um, okay, Phi composed with gamma A. Um, M 0, where M goes from 1 to L. Okay, so if you look back at the Fodde-Bruno formula, you will see that this derivative is expressed as a finite linear combination. In fact, the number of terms in the finite linear combination is J. Okay, of lower. And I should say here that L and L is less than or equal to J. Okay, of terms which involve the derivatives of the overlap map of order less than or equal to J applied to vectors which are derivatives 1 up to Lth derivatives of this thing. Okay, so there's some complicated formula which is combinatorial in nature, which tells you what these V's are. Okay, but I don't want to go back and dwell on the details. The point is that what you prove inductively is that, again, this is true if and only if this is true. Okay, and again, the k equals 1 case follows from the tangent bundle case, and then you inductively prove that it's true for any j up to k. All right, so there's a complicated argument that you have to do there. And it's not hard, but it's just a bit tedious. All right. Okay, good. And so I won't write out all the details there. And we're gonna look at that formula a little bit more closely later. Okay. All right. And so but the punchline is that this definition of equivalence is independent of chart. Okay. Of course, it has to be. And so we wouldn't be making the definition if it wasn't. Okay. The kth order tangent space at x naught, of course, is the collection of all kth order tangent vectors. Okay, so that's the generalization of the tangent space, the kth order tangent space. All right, so we're going to do now the same thing for the kth order tangent space as we did for tangent spaces, and that is we're going to define a bundle of these things, which is going to be the kth order tangent bundle. Okay. Sorry, just give me a second here. Okay. All right. Um, right. So now let's look at the higher order tangent bundles, not just the um, tangent spaces. Okay, and the definition is rather the same as the definition of the tangent bundles. So the notation I'm going to use for the kth order tangent bundle is this. Okay, and sorry, I didn't give the notation for this. The kth order tangent space I'm going to denote like this. Okay, and so the kth order tangent bundle is the collection of all kth order tangent spaces. All right, so again, there's no difference in the definitions here conceptually. Okay. So when do we start seeing some differences? Well, we start seeing some differences when we talk about the structures of these things. Um, so let's look at the the structure of T, K, M. Okay. Because it's quite intricate, and I won't sort of go through everything that's required to outline what this structure is, because there's a lot of stuff you have to say, but I'll say in words what the main ideas are, and the rest of it is written out expansively in the course text. So first, let's look at the differentiable structure. Okay. All right, so first we're going to do the same thing as we did for the tangent bundle, and that is given a chart, U, phi, phi, v, phi, for M, we're going to build a chart for TKM. Okay. And the definition is rather what you would expect. So, it's one of these situations where if somebody forced you to say what these symbols meant, given all the constructions we made so far, there's only one possible choice, and this is it. Okay, so we denote by TK U phi to be the collection over U phi of all the higher kth order tangent spaces at these points. Okay, T K V phi is going to be the K plus one fold product of V phi. So V phi to the K plus one. Okay, so this is V phi cross V phi K plus one times. All right. And so in the case when K is equal to one, so that's the case we've already done, the tangent bundle, this is V phi cross V phi. So that at least agrees, the counting at least agrees with what we already have. And then we're going to define T K phi to be a mapping from T K U phi into T K V phi. Sorry. Well, I guess um, uh, okay. Um, So I should have mentioned up here the notation I'm going to use for equivalence classes. So an equivalence class I'm going to write as gamma k x naught is going to be an equivalence class. Right? So that notation I think makes sense. And the k equals 1 case is the one we already had. All right, and so t k phi of gamma kx. All right, so it's going to be a typical kth order tangent vector in here. All right, so that will have the kind of obvious definition again. So, um, right, so this is a k plus 1 fold product here. And, the first term in the product is going to be this one corresponding to the chart. And then the remaining k terms in the product are going to be uh, um, these derivatives, okay? The first k derivatives of gamma composed with phi, right? So again, it's going to be phi of x, phi composed with gamma 1 at 0 up to phi composed with gamma k at 0. Okay, so the first k derivatives of the curve as it passes through x naught at time 0. Okay, all right, so then, okay, so so if A is an atlas for M, okay, then TK A, and of course this is going to be the set of all TK U phi, TK V, TK V phi, such that U phi 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 is a chart in the atlas. This is an atlas for TK. Okay. All right, so now we're going to look at the overlap condition a tiny bit more carefully. All right. Um, all right. Uh, okay. Um, so let's first think about what it takes to prove that each of these things is a chart. Okay. So we're going to show, we're going to claim that T K phi is injective with T K phi of, so its image, T K U phi, is going to be phi of U phi in the first component, and then everything else is unrestricted. Like that. All right. So in the tangent bundle case, when k is equal to 1, it was just U phi cross V phi, but now we have the first k derivatives, not just the first derivative. All right, and the idea of this is it's rather the same as it was for tangent bundles. What we so injectivity, and so I'm going to skip some details of this completely trivial argument and just say injectivity follows from the definition of equivalence of f k curves. Okay, so immediately, if you take um, uh, 2 points in here, which are different, okay, you need to show that their images are different. And so um, if they're the same, then what you just immediately from the definition, and from the definition here, I mean the definition of TK phi, you can see that if two curves have the same image under TK phi, then they're going to be equivalent because you're going to have, gamma 1 and gamma 1, gamma 2, and those things have to be equal, and so the curves have to be equivalent, and so therefore they had to be the same curve. Okay, so that's injectivity. All right, so showing that the image of uh, the image of TK phi is all of this is again the same idea as we had when we looked at k equals 1, and that is for every point in here, you explicitly construct an equivalence class of curves which maps to that thing. Okay, so to show that TK phi is onto phi of u phi cross v phi to the k. All right. Let's say phi of x, v1, vk, be a point in phi of u phi cross v0 k. All right. And so what I need to do is I need to find an FK curve gamma at x naught, or at phi inverse of x, that maps to this thing under the chart map. Okay, so define. And again, it's obvious how you do this. Define gamma of t to be. All right, so you take a curve, first of all, in here, okay, which has the appropriate derivatives, okay, namely these guys, all right? And so that curve is just going to be phi of x, right? Because it has to start at phi of x at time t equals 0. And then you're going to go plus t v1 plus t squared over 2 factorial, v2 plus t to the k over k factorial vk. All right, so that you can very quickly check that this thing as a function of t, when you differentiate it j times, where j goes from 1 to k, and then evaluate that at t equals 0, you simply get exactly vj. All right, so it's contrived to give you that, and then you go phi inverse of that thing. All right, so that gives you now a curve in M. Okay, and this is valid for t sufficiently small. So in some connected neighborhood of 0, for example. All right. All right, so the point is then we have t phi of gamma k phi inverse of x is equal to phi of x v1 vk, right? So that shows surjectivity. Oh, sorry, tk. Yeah, okay. All right, so now the overlap condition, okay? And we've already kind of talked about this because this is really what the argument was when we talked about um, all right, so let me just say so this shows that T K U phi T K phi T K B phi is a chart. Because all it needs to do to be a chart is it needs to be injective with open image in the chart codomain. All right. All right. So now let's consider the overlap condition. Okay. So what we're going to do is so this really amounts again, as I said before, this amounts to the chain rule. Okay, so what I want to do is I want to just sort of fill in a few more details that I didn't quite fill in last time about what the overlap condition looks like. Okay. Um, not sorry, when not last time, but when I talked about this business up here, I was kind of chatty about it. I'll be slightly less chatty about it here, and we'll try to sort of flesh out a little bit more what that overlap condition looks like. Okay. All right. So as we saw above, when considering the chart independence of equivalence. Okay. Um, uh, we have so let's if we have two charts again U phi 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 and U psi psi phi psi are overlapping charts. Then the overlap map. Okay, so T K psi composed with T K phi inverse. All right. Okay, so that's going to take a point which looks like X, V1 up to VK. All right. And what's it going to do? It's going to map it to, okay, so it's going to map it to, and here, what are the V's? So VJ is so it's going to be the image of some curve, and so it's going to be phi composed with gamma j at 0. Okay, so every v will necessarily uh, look like this, as we've already seen. Okay, but in the previous when we showed that that t k phi was surjective, every v must necessarily look like this. All right. Um, and so this thing is going to look like this. So it's going to be psi composed with phi inverse of x. It'll be the overlap map for m in the first component. Um, and then it's going to be psi. Okay. So when you take this thing and you map it backwards under t at TK phi, it's going to be some curve, okay, or equivalence class of curves, and then you're going to take that same equivalence class of curves and map it forward by TK psi, right? So the equivalence class of curves comes from this formula here. So there's a curve gamma that's implicated in the specification of V1 up to VK is the point. Okay, so you get that same curve. Right, so that's what the overlap map looks like. But that's not that doesn't give you enough information um, to prove, for example, that it's a diffeomorphism, right? So let's expand that a little bit. So we do the same thing as we did previously. You do this chart insertion business where you stick a phi composed with phi inverse in between um, the psi and the gamma. Okay. Okay, so note psi composed with gamma is psi composed with phi inverse composed with phi composed with gamma. All right. All right, so now, and so as I said before, note that psi composed with gamma j is uh, going to be now I have to again use the Fa de Bruno formula to give an explicit formula for this. Okay. And I'm only going to give you the first couple terms is the point. Okay. And note that this, and note that is given, and I just want to give the first few terms to give you the main idea about what this overlap map looks like, given by Fa de Bruno. Okay, and the first, let's look at the first three terms. That'll give us some idea about how this works. Okay, so D uh, psi composed with gamma. Oh, sorry, the first derivative. Apologies. Okay, so psi composed with gamma 1 at 0 is, well, this is just the ordinary chain rule. So this is D psi composed with phi inverse at phi at x, the way I've written it. Okay, and then okay. And so then the chain, so let me write it out just sort of temporarily here, right? So I'm going to get uh, the derivative of this, which I have here. And then in the second slot here, you're going to put the derivative of this, right? So it's going to be d phi composed with gamma at 0, yeah, at 0. At 0 and 0, 1. Okay, um, that's how these derivatives are defined. Okay, so you had homework problems where you calculated these higher order derivatives, and so you had these formulas. And again, I won't write this out, but I'll write it out in disappearing ink. So you had that uh, gamma j at 0 is equal to gamma j at 0 is equal to d, d gamma dj at 0 with a 1, 1, 1, 1 in here. Okay, and generally you had a formula here where it was A1 up to AJ, and then you had the A's which showed up out front here, right? Okay, so you had a homework problem to do that, all right? So I'm using that homework problem here, and the point is you just get here, you simply get V1. Okay? All right, so this formula is hiding the chain rule because it's using the fact that phi composed with gamma prime at 0 is equal to V1. Okay, so I'm making that substitution. All right, and I'm going to do the same thing now for the second derivative. So psi composed with gamma 2 at 0. Okay, so you use the chain rule again. All right. Um, and what you get is you get that it's d psi composed with phi inverse at x. And now what you get is v2, okay, plus d2 psi composed with phi inverse of x sorry, v1, 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 like that. Okay? And so now where does this come from? Okay. This comes from, well, I had previously kind of fumbled a bit over this when I wrote down these second order chain rule calculations. But this comes from that calculation. If you look back at that calculation, then you can see that this is what you're going to get here. And again, we're using the fact that this is true. Okay, so we're making this substitution here. All right. And then, so like I said, I'll do the first three of these. So psi composed with gamma 3 at 0 is, right? So this one, and they get longer and longer. Okay, so it's d psi composed with phi inverse of x v3. Okay, that's the first term. Then you get plus 3 d2 psi composed with phi inverse applied to x sorry, v1, v2. All right. And then d3 psi composed with phi inverse of x, sorry, x comma v1, v1, v1. All right. Okay, and all of this is just Fa de Bruno. Okay. All right. Now, what do I want to observe here? Well, I want to observe, so what I had sort of said when we talked about proving equivalence. Oh, sorry. Sorry, I don't. So the question is, could you? I assume you meant, can you explain why you have to prove the overlap condition? Is that what the question is, Bianca? Um, right. So when you define it's not enough when you define a manifold structure, it's not enough to just cover the manifold with charts. That's not enough. You have to also show that the overlap conditions hold between the charts because that's what makes your collection of charts that covers the manifold an atlas. Because it's possible that you can cover it with charts, and maybe two of those charts are not compatible. So let me give you some weird instances, and these are not meant to be understandable within the context of this course, but to give you some idea of the strange things that can happen. So in the homework, there's a simple example of where this can happen. So for example, there's an example in the homework where you have R2 and you cover R2 with charts. But the charts are defined with values in R. Okay. Um, but you can also, of course, cover R2 with charts with values in R2. Namely, you can cover R2 with the identity chart. So you have these two, two different collections of charts, but they're not compatible. That's kind of an uninteresting example. There's interesting examples that can happen. So I mentioned this before, and I'll mention it again, that for simple manifolds like spheres, so not infinite dimensional, nothing funny going on there, you can, um, uh, for certain dimensioned spheres, and it's kind of understood what dimensioned spheres they are, and the lowest dimension sphere is the seven-dimensional sphere. So this is all very mysterious, and I don't pretend like this is explainable by me, and certainly not here. Um, the seven-dimensional sphere you can cover the seven-dimensional sphere with a bunch of different kinds of charts, and they are not compatible with each other. So these kinds of examples show you why it's just not enough to cover the manifold with charts, but you have to show that the charts are compatible with one another. And that's what defines a differentiable structure. So it's important to keep in mind that a manifold is not just a covering by charts. It's an atlas. It's defined by an atlas, and the atlas defines a differentiable structure, and it's very possible that the same set. Okay, so a set is not a manifold. Manifold is a set with a differentiable structure. So you need to define a differentiable structure, you need to find an atlas of compatible charts. So that's I hope does that answer the question? Okay, good. Um, all right, so and sometimes um, when you're working with simple examples, it can seem really tedious to have to verify that, the thing that the collection of charts you defined as an atlas, because it just seems kind of obvious. And more often than not, it is, because many different manifolds are, they're kind of, the differentiable structures are kind of unique. Um, uh, but if you're looking at a manifold for the first time, in other words, it's not a classically known example of a manifold, then you should probably think a little bit about the differentiable structure. Okay, and so here we have a manifold, and the differentiable structure is kind of complicated. Because we can see here that the overlap conditions are kind of complicated. And you look at these, and it's not immediately clear that these are um, that these things are CK diffeomorphisms. Okay, but let's see now why they are. Okay, so let's suppose that we're in the case of k equals, well, let me just look at the case of k equals 2 to keep things simple. Okay, so what we want to show is we want to show that if we take this overlap condition, and so this is the overlap condition, J here goes from 1 to 2, okay? And so for J equals 1, this is how this thing is defined in terms of our original chart coordinates. And for J equals 2, it's defined like this, okay? And so I claim that that thing is a diffeomorphism. So why is that the case? Well, again, you do this kind of by induction. So you look first for the case of J equals 1, and in the case of J equals 1, we've already seen that this thing defines a diffeomorphism from phi of u phi cross v phi to psi of v psi cross v psi. Okay, so we've seen that already in this case. All right, so we know that we're good there. All right, and so what this means is that um, uh, uh, the dependence of this thing on X and V1, okay, is such that the overlap map here is a diffeomorphism. All right, so now let's look at the case of the J equals 2 case. All right. Okay, so for the J equals 2 case, it's a sum of two things. All right, so this one, all right, we already know that the dependence on x and v1 is smooth. We already have that from j equals 1. Okay, so really all we need to do is look at the dependence of this term. Okay, but the dependence of this, so notice that this highest order term, and by highest order I mean involving the highest v, okay, because the v's, remember, are the derivatives of the curve. Okay, so for the highest order term in the derivative of the curve, this thing is exactly like this thing. Okay, and so you essentially take, you can take this and sort of move it over to the other side, and then you see that the dependence on x and v1 and v2 is now a diffeomorphism in x and v1. Okay, and so that's how you kind of ratchet this up order by order. Because again, you always see that the highest order term is the same as the first order term. Okay, and then you get these nonlinear terms that appear with the highest order derivatives. And by nonlinear, I mean they're nonlinear in the v's. Okay. All right. Um, um, and so and so the point is that after all that settles, and and again you have to do a careful inductive proof to do this properly, which I'm not going to go through, because essentially it's what I just said. So the punchline is that t k psi composed with t k v inverse is a, so what how smooth a diffeomorphism is it? Well, if the manifold structure is CR, okay, so we're losing a derivative at each step here, right? Right, so you have a second derivative here and a third derivative here. So it's actually it's a CR minus K diffeomorphism. Okay. All right. And so that's the overlap condition. Okay, so thus um, T K A defines a C R minus K. All right, so if the manifold is CR, its kth order tangent bundle is CR minus K. So you lose an order of smoothness for every time you have to differentiate to get tangent vectors. That kind of makes sense, I think. Okay, so that's the manifold structure. Okay, so the overlap conditions are now these kind of complicated overlap conditions, the first three of which I've written out here. Okay. Um, so we saw that Tm, the tangent bundle, is a vector bundle. And how did we see that? We saw that in a very specific way, and that Ta is a vector bundle atlas. If A is an atlas. Now, is the kth order tangent bundle also a vector bundle? When k is greater than or equal to 2. When k equals 1, obviously it is. Okay. Well, these are questions you always have to be a little bit careful of. So if somebody asks you, is something a vector space? right? Well, the answer is maybe, but you have to tell me what the vector space structure is. Um, it's hard to prove that there's some sort of cardinality-based arguments you might be able to use to show that certain kinds of sets, can't be, for example, real vector spaces. Um, but in general, if you're given some set and you want to show that it's not a vector space, that's hard because you have to know what the vector space structure is. And this is a question of the same form, right? Um, so I'm saying it's not a vector bundle, okay? But is that true? So the question is, are all tangent bundles vector bundles? Yeah, they are. So in the case of k equals 1, um, this atlas that we constructed last time is a vector bundle atlas. So we verified that last time. And so it's always the case that when k equals 1, Tm is always a vector bundle. Okay? But, okay, good. Um, and so the structure of TKM when K is greater than or equal to 2 is a little bit more complicated. And so let me answer the question like this. This is not a vector bundle atlas for K greater than or equal to 2. Okay. All right, so that's the answer to the question is this a vector bundle? Actually, you can put a vector bundle structure on it, but it's not that vector bundle structure. It doesn't have a canonical vector bundle structure. So this atlas that we have put on here, this atlas is oh, sorry, I didn't mean TK. I meant um, that. Okay, so this is a canonical atlas that comes from an atlas for M and gives us an atlas for TKM. All right, and that atlas is not a vector bundle atlas. So that's the proper answer to that question. This question isn't actually perfectly well defined, right? But this is a well-defined answer to that not very well-defined question. Okay. You have to be careful with all these kind of questions about is this thing this kind of an object, because depending on what structure you choose. So why is this not a vector bundle atlas? Okay, well, we've seen that already. And so there's some, if M is a zero-dimensional manifold, then I suppose it is a vector bundle, but that's not very interesting. Okay, so there's some non-degenerate cases I'm omitting here. But we can see here why this atlas, TKA, is not a vector bundle atlas. In order for it to be a vector bundle atlas, it should be linear in um, these bits. Okay, so it should be linear in V1 up to VK, right? But it's not, right? So the first derivative is certainly linear in V1. The second derivative, it's linear in V2, but not linear in V1. The third derivative is linear in V3, but it's not linear in V1 and V2. Okay, and that general observation holds for all derivatives. So the fourth derivative, so in general, the kth derivative is linear in VK, but it's not linear in any of the other V's. All right. Um, um, and so it's, because it's not linear in all of the V's, it can't be a vector bundle atlas. Okay. All right. So we can see above that T K psi composed with T K phi inverse of X V1 up to VK is linear in VK. but not linear in V1 up to VK minus 1. Okay. We at least see that for the cases k equals 2 and 3, and it is true in general. But that involves digging a little bit into involves checking some stuff with the Fodde-Bruno formula. Okay, so um, so the punchline of this is that T K M does not have a natural vector bundle structure. It generally speaking will have a vector bundle structure, but it depends on another choice of thing like a connection or something like that. Okay. All right. But there seems to be some kind of remnants of linearity here, so it's linear in the highest order derivatives. Okay. Um, and so in fact, what's true is that and I'll write something out here without saying what all the words mean, but just to sort of say that it's not like this thing has no structure at all. Okay. So note, however, that we have projections, and let's call them maybe pi m k l from t k m to t l m, as long as l is less than or equal to k. Okay. And so this is just saying that if you have a kth order tangent vector, all right, so that means curves that are equivalent up to order k, then you also have an lth order tangent vector, because if it's equivalent up to order k, then it's also equivalent up to order l. And so you have equivalence up to order k gives you equivalence up to order l. All right, so you have these projections like this. And so you can organize these things into a diagram. Oh, sorry. Uh, yeah, sorry. Let me just do it like this. Let me do it horizontally. T K M T K minus 1 M, right? Like so. And then down to TM, which has its projection onto M. Okay. And so our observation when we looked at these formulas here again was that the highest order derivatives, it was linear in the highest order derivatives. Okay. So what this means is that there's somehow some linearity if you fix, let's say, the derivatives of order k minus 1 and only vary the derivatives of order k, right? So in these formulas here, that means you, for example, here you fix v1 and you only allow v2 to vary. Okay, and here you fix v1 and v2, here and here and here, and you allow v3 to vary. Okay, so there seems to be some structure there. So it's linear, and then you have this other stuff. And so that structure is, and T K M over T K minus 1 M. So it's not a vector bundle, but it's what's called an affine bundle. And if you are familiar with the term affine map, so an affine map means a map which is linear plus constant. Okay, and you can see that these maps are indeed, if you, again, if you fix if you only allow the top order derivative to vary and fix the other derivatives, then this is an affine function, right? It's linear plus constant, right? Linear plus constant, right? So that's where the affine bundle structure comes from. So, you have to define what affine bundle means, and that's done in the course notes, but I'm not going to talk about it here. Um, affine bundle. Okay. So there is some structure. It's not quite the structure of a vector bundle, but there is some structure. Okay, good. So those are the higher order tangent bundles. All right. And so this shows you why. So, I always said if you have if you cover your manifold with charts, or I also said vector bundle charts, that does not mean that your set uh, is made into a vector bundle. Okay, and this example here is a good illustration of why. Okay, so we have these mappings TK phi from TK U phi into, so let me write it out explicitly here. So it's phi of U phi cross V phi to the K. Okay, so we have mappings whose codomain, and it's more than that, okay, um, that are bijections onto local vector bundles, right? So this thing here is a local vector bundle, right? So it's an open subset of a vector bundle cross a vector space, okay? Are bijections onto local vector bundles. And your inclination is to say, if I have established around any point a mapping which maps some neighborhood of that point into a local vector bundle, then I've established, and this is kind of an answer. It's not about manifolds, Bianca, but it's about vector bundles. And so this is sort of another illustration of why you need to verify the overlap conditions, because although this mapping takes this set and maps you bijectively onto a local vector bundle. And so by the sort of rule of, well, obviously then my object must be a vector bundle because locally it looks like a local vector bundle, but it's not true. Okay. Okay. But this does not give a vector bundle structure. Okay. Right. So this is a good sort of cautionary tale about why you should verify things. Okay, because sometimes, and this is very often true with vector bundles, that you build things that are in bijective correspondence to a local vector bundle, but that does not mean that your object is a vector bundle. Okay, good. So that's the structure of higher order tangent bundles. So now what we want to do is we want to take all of this stuff that we've now talked about, um, and use it to talk about derivatives of mappings between manifolds. So we've talked about um, what it means for a mapping to be of class CR, right? So it's of class CR if its local representatives are of class CR. But we haven't actually said what the derivative, so if you have a mapping that's of class CR, you should be able to talk about its first derivative, its second derivative, up to its rth derivative. Um, but we haven't done that yet. Okay. Um, so let's see how you might do that. All right, so let's let M and N be CR manifolds. Okay, let's let K. All right, so we're gonna, allow uh, um, various degrees of differentiability and derivative here. All right, so we're going to let K and M be um, non-negative integers, um, sorry, such that, okay, so K is going to be less than or equal to M. It's going to be less than or equal to R. Okay. Okay, so I'm now going to take a mapping. So my manifolds are of class CR, and R could possibly be infinity here. Okay, but K and M are non-infinite, non-negative integers. Okay, and I'm going to take a mapping, which is of class CM. Okay. Okay, so then we have some things that are true. Okay. So the first thing is that if gamma is an F, sorry, K curve at X naught, okay, then phi composed with gamma is an FK curve at phi of X naught. All right. So as we'll see that this is important for the definition that we're about to make. Okay. So the mapping. Um, so it's the kth derivative of the CM mapping, sorry, phi. So this is going to map the kth order tangent bundle of M into the kth order tangent bundle of N. And so it's going to take a curve with its equivalence class to order K at X, and it's going to map it to the equivalence class of that curve composed with gamma to order K at phi of X. All right, and this definition makes sense because of part one. Okay, so if part one holds, then this construction at least makes sense. Uh, um, so this is an equivalence class of curves to order K at X, and part one says that this has a well-defined equivalence class to order K at phi of X. Okay, so this mapping, moreover, is a M minus K. All right, and it has structure with respect to this affine bundle structure that I talked about before, but I won't talk about that here. Okay. All right, and this is really just again, it's just an application of the Fodde-Bruno formula, and so I won't sort of waste any more time talking about um, derivatives of compositions since I think we've spent enough time talking about that. Okay. All right, and so that's my proof, which I hope you found extremely convincing. All right. Um, and this thing is what is called the kth order tangent map of phi. All right. Okay, so I think rather than try to race through, um, so there's an important example to do here. It's not important because it's um, manifestly important in that it says important things, but it's important because it establishes a connection between higher order derivatives that we've talked about previously. All right, so previously we talked about, if you had phi as a mapping between an open subset of a locally convex space, um, U into a locally convex space V, we had defined these things. And this was a mapping from O cross U to the K into V. All right. And so what we want to do is we want to establish the connection between this and this. Okay. And the connection is not just as simple as you would like it to be. And so we'll talk about that maybe next time. And I'll also maybe say here, so there's three more lectures left um, in the course. And what I will do is I'm going to do the next lecture sort of ordinary, sort of going along as I have been. And then for the last two lectures, what I'm going to do is I'm going to smush through a pile of stuff. And it's really the point of the pile of stuff is going to be to give you some idea of the kinds of things that you can do with all this technology that we've developed. So the emphasis will be on I'm not going to say applications uh, because applications of this stuff require significant work just to do the most basic things. All right, but to talk about things which at least point in the direction of applications of this technology. And so developing some tools that will directly be useful to, solve, kind of, for lack of a better term, real world problems. Never liked that word, um, but we'll talk about that. So the last two lectures, I'm going to, first of all, for example, I'm going to write out the lecture, so I'm not going to write it out live. I'll have the lecture prepared beforehand, so we're going to go fast. And it'll be at a very high level, but hopefully it'll still be enough detail to comprehend what's going on, and we'll be able to sort of get somewhere at the end of the course where we can hopefully say some interesting things about things that are interesting. Okay, so that'll finish it for today, unless anyone has any questions. Okay, bye-bye.